Hello, it's Keith here, and this is lesson 4 of my ARM assembly programming tutorials. This week we're going to be looking at the stack. We're going to discuss how the stack works in practical terms on the ARM, and we're going to also briefly look at the SWI command, which you will need if you're doing operating system programming on RISC OS. It's not something I tend to use very often because I tend to try and go directly to the hardware and avoid using the operating system, but it's an important command to discuss on the ARM, so I thought today would be a good place to slot it in. So first of all, we're going to discuss the stack. Now, if you're familiar with other assembly programming languages, you're probably going to know what the stack is, but if you're not, don't worry, because we're going to go over the concept of the stack and how it works on the ARM, so you'll be absolutely fine if this is your first time with that concept. Now, with assembly programming language, very much so in 8-bit systems, not so much with 16 and 32, but 8-bit systems, you often needed the stack as a temporary store for variables because our registers, we had very, very few of them, and on the 6502 we literally only had 3. So we needed a way of backing up and restoring values very frequently within our subroutines. Of course, this is still going to be true on a system like the ARM where we've got a lot of registers. We're still going to need to be able to back up and restore data, even if just so that our subroutine doesn't corrupt all of the values in our registers that the calling program actually needed. So we're going to need to back up and restore things, and the stack is the way we do this. Now, I usually refer to the stack and ask you to think of it as an in tray in your office. If you're working on a bunch of tasks and someone wants to give you a bunch of new tasks, you might put your old tasks, the paperwork, into your in tray, and then if you're working on those tasks and someone wants to give you more work to do, you might put those on top of the in tray again. And each time you finish a task, you then start taking the paperwork out of the top of the in tray so that the first thing you take off the top of the in tray was the last thing you put in. So you're repeatedly putting paper into the in tray and then taking it off in the reverse order, so to speak. So the last thing you put in is the first thing you take out. Now, that's basically the concept of a stack. The stack is a stored area of memory in the system, and we have a stack pointer, and every time we push data onto the stack pointer moves down in memory. So if it started at 1000, it would decrease going towards 0. And on the ARM processor, every time we push onto the stack, we're pushing 32 bits, the entire width of the register. So the stack pointer will be going down, and as we push items onto the stack, the value that was contained in that register will now be stored on the stack. This is effectively backing up that register so that we can do some other work, and then when we restore the value of that register, the value is popped off the stack pointer moves back up to its original position before the value is pushed on, and the original value that register contained will be restored. So that's the concept of stacks, and we will be looking at that today. So if you think of your stack as an in tray, or alternatively as those sort of coin keepers, you know, the ones with the spring in, and you push a coin in and then it goes down, and you push another one in and it goes down, and then you pop the coins back off. And that's effectively how the stack works. We are always taking the values off in the reverse order till we put them on. So the last one that we put on is the first one we take off. And the stack, typically speaking, goes down. Now, in the case of the ARM, actually, we do have other options. We don't need to work in that sense, but that is the normal way. And so that's what we're going to be looking at today. We're going to be doing all of this with practical examples. So let's go over to our source code and let's see them in action. Okay, so here's the source code we're going to be working with today. Now, the ARM, like the 68000, doesn't have a push and a pop command as such. Now, on an 8-bit system, the Z806502, we have a command that's a push and a pop or a push and a pull or something like that. But with the 68000 and with the ARM, the addressing modes that the processor contains are so advanced that we don't need a dedicated command to do the pushing and popping action. We can actually do it with the normal addressing modes, and we can actually do it with any register at all. Now, the stack pointer is defined as a sort of known symbol here, so we're going to be using the stack pointer, but in effect we could actually use any of the registers as a functional stack. It's just that R13 is the one that's defined by the system as being the one that we are using as our main stack pointer. Okay, so we've got this code that we're going to use, and it's got some functional macros here that are going to do some operations for us to show the results of what's going on. We're not going to discuss how those macros work today. We're just going to discuss the concept of the stack in itself. So let's just fire this code up here. Here we go, it's loaded up there. And if we just move it over here, and we'll just lock it onto the top of the screen here so we can look at it and discuss it at the same time, and we'll see what's actually going on here. So we've run this test push an item function here, and this has loaded in a test value here, FFEEDDCC, into R0, and you can see that just there. Now we've dumped the actual memory that is being used by our stack just here. Now when our program starts, the stack pointer will be given a value by the operating system, and we don't really know what that stack's going to be, but it doesn't actually matter for this case. All we need to know is that the stack pointer started at 854C here, and this is the contents of the stack. Now when the stack starts, the stack pointer is effectively pointing to this position just here. So these are where the values that we're going to be pushing are going to appear. So we're going to push an item onto the stack. We're going to push R0 onto the stack. Now the stack pointer always moves down when we push. So because we're pushing 32 bits onto the stack, that's effectively 4 bytes. So we want to subtract 4 from the stack pointer, store the value onto the stack, and then update the stack pointer. And that's what this command does here. Now if you remember the addressing modes tutorial we did, the exclamation mark at the end tells the processor to update the register, the stack pointer, and the -4 here is going to be subtracted from the stack pointer before we do the write. So the stack pointer is here, we subtract 4, we then write the R0 value, and then we update the stack pointer to this position. So that's the procedure that's going on with this command just here. And this is effectively just the same functionality as the push command was on the Z80. So it looks a bit more complicated, and we could create a macro to do this for us. That would be a lot more convenient, but I like to avoid doing that for the commands when I'm explaining them, because I want you to see what the process is really doing. And if you jump in halfway through these tutorials, I don't want you to see macros that I'm relying on that don't exist, where I can avoid it. Sometimes I have to do that, but as I say, in this case, I want to show you the command that's really happening, and this is the command. We're storing R0 into the stack pointer after we've subtracted 4, and we're updating the stack pointer. So the stack pointer is now ready to receive another value if we want to. So here we've moved 0 into R0, and you can see that just here, and we've shown the contents of the stack. Now the stack pointer pointed to here, that was 854C. We've then subtracted 4, and the stack pointer has become 8548 here. And you can see we've pushed the value that used to be in R0 onto the stack here, CCDDEEFF here. Now that's in little endian, so it's backwards, but you can see the value is there. And then what we've done next is we have done the reverse command, and we've popped the value of R0 off the stack. And the way we do that is we take the value from the address SP, and then we add 4 to the register SP, moving it back up to the next position if we were going to do another pop. And because this is a post increment, there's no exclamation mark, because we're reading from the original value of SP, the address in SP that is, and we've loaded R0 here. And you can see R0 has regained its original value because it was wiped to 0 here, and the stack pointer's moved back up here. Now one thing I do have to point out about my code here is the code itself is using the stack. So the CCDDEEFF has vanished from here, but that's not because of this command, it's because of the internal workings of the show stack plus R1 command. So unfortunately that's a bit of a limitation of my example here. If we'd got a monitor that didn't use the stack itself, if we'd got like a proper hardware monitor, then we would have actually seen CCDDEEFF still here, but the stack pointer would now be pointing back to here. You can see the stack pointer is now pointing to the same position as it was before this command ran. So that's how we can use the stack pointer to restore the value of R0. And we would want to do this if the value R0 was being used for another purpose here and we needed to restore it later. Now, of course, because these are just general move commands, it's very obvious, hopefully, that we don't need to restore back into the same register as we pushed originally. So if I just do this and run here, well, you can see we pushed R0 onto the stack. It was just here, but then we popped it back off into R1. And that's of course totally legitimate, and there's going to be lots of times you may want to do this. You know, maybe your code needs R1 to have the value here and R0 to have it here. Now, of course, if you just wanted to move a register value from one to another, then you would want to use a move command just and transfer between them. But there will be times potentially where you need to clear all of the registers, and then you need that old value back, but you want it back in a different register. Totally legitimate to do that. So that's perfectly fine. No problem doing that. Now, that's our first very simple example of just pushing a single item onto the stack, but there's no reason we actually just need to do a single item. Of course, we can nest these. Now, I tend to put tabs in whenever I'm pushing multiple items, because we want to make sure we take everything off the stack that we pushed onto the stack. We really need to try and keep things balanced and make sure everything is in order, because it's a last in first out. We want to make sure that we understand what values we're actually getting back and we don't get confused. So I find putting extra tabs in makes this nice and clear for me, and so that's the way I've done things. But this is totally optional. These tabs are just visual for me. The code doesn't rely on it, whereas the code will understand anything at the far left as being a label. Any extra tabs it doesn't care about. So that's just something for me to make clear to you. Don't think that there's any functionality there in those extra tabs. Okay, so here's our code. So this time we're going to do multiple pushes just with the same command, storing into the stat pointer after subtracting 4 and updating the stat pointer for the pushes, and the pops here loading back, and we're just using R0 each time. So what have we done here? Well, here's our starting values. Here we've got FF, EE, DD, CC here in R0, and the stack is in this position. We've then pushed R0 onto the stack and loaded a new value, 1, 2, 3, 4. You can see 1, 2, 3, 4 has been loaded here, and CC, DD, EE, FF is here. And then we've pushed R0 onto the stack again and loaded 0 here, and you can see 0 is here. And now 1, 4, 4, 3, 3, 2, 2, 1, 1, reverse of this little engine, remember? And so you can see each time also the stack has gone down from C to 8 to 4, going down by 4 each time. So this code here is the code that's doing this just here. And then we're popping back off the stack twice, and we're getting our original values back. So our 1, 1, 2, 2, 3, 3, 4, 4 is just here, and our FF, EE, DD, CC is just here. And this is why I tend to put these tabs, because we would struggle to get the CC, DD, EE, FF value in this pop, because it's going to come off in this one. Now, we can do more clever offsets and things to get the other values on the ARM, but as I say, generally speaking, we're going to take things off in the reverse order we put them on. So that's how we can nest, and that's how we can store multiple values and return them back in the reverse order. And as I say, in your code, you might need to have a loop where the loop is processing a bunch of items in an array, let's say enemies in a game, and then when you process one enemy, you may need to do a bunch of subroutines for that enemy. For example, the enemy may decide to shoot the player, or the enemy may have been killed and you need to process the death of the enemy. You may need those same registers that you were using for your loop for other purposes during that sub part, and this is how you would do it. You would push the values for the loop, do your subroutine, and then restore the values for the loop with pops. So this is how we use pushes and pops in the stack to actually do things within a game or another program when we have a small part that needs to have its own functionality, and then return to the main functionality of the main code. So you can see there we can use nesting to allow us to back up and restore multiple values for different subsections of our code, and as I say, I've put those tabs in there. Now, in that case, we pushed two registers in two separate parts. They both happen to be R0, but of course they could have been R0 and R1 at different stages. But the ARM actually has some very nice routines to actually cope with multiple commands for us anyway. Now, we're going to look at a command called stmfd, and this is actually going to store multiple registers in the same go. Now, first of all, let's go over to our other screen and let's just have a look at the options, because this isn't the only kind of command we have. Now, on most systems, the stack always goes down and we're always decrementing before we write a new value. Now, with the ARM, although this is the way we're working in this example, there are other options. So there are multiple types of stack. We can have a descending stack that goes down the memory range towards 0, or an ascending stack that goes up the memory range. As I say, the normal one would be a descending, and that's what we're looking at in these examples. There are also two kinds of stack with regards to the type. There's what's referred to as a full stack, and this is where the current stack pointer points to the last value that was pushed onto the stack, so a full item. Or there's an empty stack where the stack pointer points to the next blank space that a value is going to be written to. Now the one we're using is descending because it's going down, and it's a full stack because we're decrementing the stack pointer before we write the new value. So the stack pointer always points to the last value pushed onto the stack. So we're using it is descending full stack, and so the multiple push command is stmfd, and the pop command for multiple values is ldmfd. It's a mouthful, but that's what it is. Now I'm not going to cover the other kinds. Being a Z80 programmer and things, I really, the other ones are just like, well, that sounds clever, but I don't need them. But as I say, they're very powerful, very good to have if you need the extra functionality. And there may be cases where these are very useful to you, and you can use these kind of commands not just for storing of temporary values. You can actually use them for sort of bulk reading of data and things. You could load in 32 bytes of data from your screen just with lots and lots of combined pop commands into different registers, and then you could convert that data and show it onto the screen or something. So as I say, so there may be cases where you actually want to use the ability to read in multiple values with these commands, not just for temporary storage but for other things as well. So as I say, they're very powerful commands. It's only fair I discuss them, but we're not going to actually test those because the functionality is just basically the same concept, just with a different way of moving. Okay, so let's fire up this example of test push items here. Now we're only going to work with two registers just here. So what have we done? Well, we've loaded our FFEEDDCC into R0 and 4321 in R1. Well, 4433, you know what I mean. And then we're showing the stack. We can see it just here, so that's quite nice. And then we've used store multiple full descending stack. We're storing into the stack pointer here, updating the stack pointer, so we've got that exclamation mark. Oops. And then what we've done is we've just loaded some junk values R0, R1 in here just to clear them out. And you can see the stack contains 1, 2, 3, 4 here. That's R1. And C, D, E, F, that's R0. And then what we've done is we've actually loaded back the values into R0 and R1 here. Now we've done it slightly differently, but you can see here that the values have been restored just fine. Now here we've specified a range. We've specified R0 to R1. Here we've specified two registers, R0 and R1. Now what's the difference? Well, quite simply, we don't just need to store two registers. We can store basically all of them, really, give or take. So we could do R1 0 to R2 here, and we could do R0 and R2 here. Now if I just fire this up here, this is going to make a bit of a mess, but it's a perfectly legitimate example here. So here we've stored R0, R1 and R2, but when we've popped back, we've actually not popped back as many values as we should have, and we've actually left some data onto the stack here. So we've loaded R0 back here, but when we've left R1 and we've actually loaded R2, which I'm not showing on the screen, but we would have actually left a value on the stack. So you can see the stack pointer hasn't returned to the correct position, and that's not a good idea because that could cause problems later on for our code. But as I say, the point I was trying to make is that the minus here actually specifies a range, whereas the comma specifies a comma separated list. And R0 and R2 here doesn't include R1. R0 to R2 here with the minus does include R1. And we can specify any permutation and combination here. We can have R0 to R1 and R3 and R5. That's perfectly legitimate. It doesn't really matter. The assembler works all of this out and it does it just fine. You can see our stack pointers all over the place now, and if our code was carrying on, we would certainly get a crash because we've taken things off the stack we haven't pushed on, which isn't a good idea. But as I say, it's just a very crude example of the kind of commands you can do here. And as I say, we can specify, the point was just to make, we can specify a range of registers, or we can specify separate registers as a comma separated list, or a combination of the two. And that's quite handy for what we're going to look at next. Now, it's also important to explain that it really doesn't matter the order that we put the registers in these lists or how we express them. The assembler is converting these, and basically each register is a bit within the final command. So the resulting order doesn't matter. It's the combination that the command expresses. So like if we do R0 and R1 as a range here, but we pop off as R0 and R1 with commas, same command. And if we specify them the other way around, it doesn't make any difference to the actual resulting command. So if we pop them off with the number order reversed in this command here, they're actually popped off in the same order as they were pushed on. It made no difference here. It really doesn't matter at all. The only thing that does matter is the actual resulting registers. So if we do R1 and R2 here, of course, well, our R0 will never be restored, as we just saw. So our R0 has not got the value, and R2, if we were showing it, would have that value. So as I say, that's something important to notice. Now, I've been sort of shouting doom and gloom about making sure you take everything off the stack you put on and doing things and keeping the stack balanced and, you know, making sure your commands match and keeping things in order. Why is it so important? Well, the stack isn't just used for temporary storage of normal register values. It's often used as part of calls, and in fact on most processors it's absolutely fundamental to calls. Now that's not quite so true with the ARM. We'll have a look at it now. Now when we call a subroutine with branch and link, the program counter is moved into the link register, and this is effectively how the processor knows where to return from a subroutine. And typically when the subroutine finishes, what we will do is we will move the link register back into the program counter being the current running command. And because the link register after a branch and link will point to the next command, the moving the link register back to the program counter effectively returns to the next command that needs to be executed. And you can see we're doing that just here. So this branch and link will move the program counter into the link register. This will do some commands, then it will move the link register back into the program counter, and that will effectively return back to the running command. So this command will run here as part of branch and link test. This one will run, but then the next command that will run will be this. It doesn't flow into nested branch and link test good. So let's just fire this up and let's see what actually functionally happens. Okay, so here's our example here. So we are starting with R0 here as 0, and we're running branch and link test here, which adds 1 to R0, very simple, and then shows all of the status. So the link register here is 8688, and that is going to basically be probably, I think it's this next command here, which is where we're going to return to. And so that link register is going to be pointing so that we can return just here. And then we're running a second time the same command, branch and link test. We're adding another 1. You can see it's gone up by 1 here. But you can see now that the link register is actually a different value here. And that's because we're now going to return to the next line down this branch and link test good here. Now, this is a subroutine, but it's more complex. Now, because when we ran branch link test, we are moving the program counter into the link register. Well, if we want to run another subroutine within that branch and link subroutine, the link register would become corrupted because the original value would be lost. So what we're going to need to do is we're going to need to move that link register onto the stack somehow. And the way we're doing it here is we're using the store link register onto the stack, and we're loading it back into the program counter, which is effectively the equivalent of this. This is our return command. And this allows us to do 2 executions of branch and link test just here without corrupting the link register, because we backed it up with the stack just here. And you can see here we've done that. We've done another 2 here. And then to prove that the code is executed just fine, we are just doing another one here. We're just loading the top byte as FF here, and you can see that's happened just here. And then we're returning by moving the value off the stack pointer, which is the link register we pushed here, into the program counter, which effectively returns, and then we're showing the results here, and that's this last line just here. So you can see this all worked okay because the link register was not corrupted by our 2 executions to the subroutine, which also used the link register here. It's a bit weird, all of this, if you're used to your Z80 and things. Effectively, this is the way your typical call on the Z80 works, because in the Z80, every time you call a subroutine, the program counter is pushed onto the stack, and every time you return, the program counter is pushed off the stack. So if you just want to be simple, then don't ever use this form. always start your subroutine with a load of the link register onto the stack and end your subroutine with a pop of the program counter off the stack. And that will be the safest for you if, like me, you're more used to the Z80. Okay, now it's important to point out that it's not necessary for us to move the link register onto the stack. We can back it up in another way if our program allows it. In this example, I am moving the link register into R9, and then I'm moving R9 into the program counter, and this will work exactly fine as well. It doesn't matter that we've not used the stack as long as another condition is true. Now, this only works if R9 is not corrupted in any other way. You see, this has worked fine because our last value shows the change, the FF change that we made just here. So our return did work okay. But if, for example, this code used R9, for example, if we just do move R9, #0 here, and we just fire this up, well, now horrible things have happened. Internal error branches, some strange code is executed, and it's caused a mess. The reason it's caused a mess is totally understandable. Well, it's because we've been doing nasty things. What we've done is we've basically corrupted our return address here because this subroutine was relying on R9 not being used during this branch and link test sub, and that's why these commands using the stack are the safest. Now, they do rely on the stack not being messed up, but that's something I think, generally speaking, you should be able to rely on. You know, I think if what a subroutine does with a register is a bit ambiguous, but a subroutine should be leaving the stack in a safe state, or at least if it's doing strange things with the stack, it should be very well documented what that subroutine is doing with the stack. So, as I say, generally speaking, that's going to be okay. Now, a system like the RISC-V has specific rules about what registers a subroutine is allowed to change and what registers it's got to make sure are still the same. I don't believe those kind of rules exist on the ARM, so you would have to kind of work out how best to work with your registers. But I think if you want to play things safe, use the stack to back up the link register in all cases, and then just worry about maybe if there's a fringe case where you want to be a bit faster and just do this kind of thing of just moving the link register back into the program counter, because either you've got no subroutine calls or the ones you've got are completely definitely safe and are always going to be safe. But yeah, you could be making things a little bit difficult for yourself further down the line. So that's the concept of the stack and how the stack affects branches. So I think that's a important thing you need to understand if you're programming the ARM. It's a little bit different to what you might be familiar with on other systems. Speaking from my experience, it was very different, but it's a good logical way of doing things. Effectively, what they've done is they've said, well, you can use the stack to back up your return addresses, but you don't need to, and that's going to give a little bit of a speed saving if your subroutine doesn't need that stack to back up that link register. Because we've got so many registers, we can actually be a bit more efficient and just store the return address in the register rather than going to the memory in the stack. Now, one other thing I do want to briefly cover with the stack is the return addresses again. Now, in the case we've seen here, we've been restoring the return address with a move command here, and we've also moved multiple registers with our examples just here, but we can actually combine the two effects. We can load the link register onto the stack with a command like this, and then we can restore the link register back into the program counter with a command like this, and this will work fine. And so effectively this command is backing up basically all of our registers and the link register, and this command is basically restoring all of our registers and then effectively returning, and that is perfectly legitimate, and it's a fine way of doing things, and it's taking advantage of the, as I said before, the registers will restore into whatever they're told to, and the order of the registers is quite sort of strict within these commands. So as long as we make sure we're pushing the link register here and restoring it here, and we've got the same number of registers in between, that's going to work just fine, and that will allow us to back up our link register and return with just two single commands here. So it's definitely worth bearing in mind. Now, the other thing I said we were going to cover is the SWI. I believe this stands for software interrupt. It's not something I've used very often, but if you're doing things with RISC OS and you're doing operating system calls, you do need to understand it. Basically, what it is it's a bit like the traps on the 68000 or the OSTs on the Z80. Effectively, they're an operating system call to a low memory area, and they will have some kind of code that will handle things. So what this code does, I can't tell you, because it's going to depend on the operating system you're using and also what we need that operating system does. So SWI 1 on the RISC OS machine is an OS write string. And what it does is it takes a subsequent set of characters followed by a 0 byte, and it will show it to the screen. We're also going to use SWI hexadecimal 11 here, which is a return to the operating system, and that needs R0 to be the error code, and we're just telling it error code 0 here. So you can see here we're passing a hexadecimal byte to this SWI. You can see it's very small here, but we've got hello world. Can I make this bigger? No, I can't. So we've got the hello world message here, and then it says press space or mouse to continue, because the SWI to operating system call 11 OS exit has worked just fine. And now we're back to our boring OS. Now, I don't think these do anything at all on the Game Boy Advance. This is really a RISC OS thing. And what you need to do is you need to go online and find the documentation of all of the SWI commands and what parameters you need to pass to them, how you need to pass them. You can see this one was passed in line just after the command, and the command will jump over it, whereas this one needed a value in a register. So it's going to be very, very varying, and you're going to have to check the documentation, and you're going to have to check your documentation matches the version of the operating system you're using, because in some cases new commands have been added. So don't be surprised if you're trying to use a command and it doesn't work. Maybe your operating system is too old, or maybe it's too new and the command has changed. We're not going to cover that kind of thing. This is an ARM programming tutorial at this stage, not a tutorial on RISC OS. We will be doing some platform specific stuff later on. But as I say, to cover the ARM, I needed to cover the SWI command, and this is how you use it. Okay, so that's what I wanted to cover for today's lesson. We've covered the basics of the stack rather quickly. I know it's a bit of a tricky concept, but don't be too scared if you're struggling a little bit with it, because we're going to keep seeing it later on, and I think it'll start to become clearer. The commands are a bit of a pain, but as I say, you could create a macro and define a push, a pop command, and a return command just to make things a bit easier, but I want to make things as clear as possible for what the process is really doing, because that's the point of this series really, is to try and understand how processes are working as much as actually programming for them. So that's the way I do things. I hope you found this interesting anyway. Please like and subscribe if you have. We're going to be doing more on the ARM next time, and there's lots more content we're going to be covering on the ARM, so please follow along for that, but also check out my other tutorials as well. I've got a forum as well if you want to chat about programming or just retro in general. Please see my website for that. I've now got learnasm.net, which is my new easy to remember name hopefully, so please go along and join the forums, because I have little programming competitions for fun and give away little prizes and things as well, so check that out. Anyway, I hope you've enjoyed this. I hope you're going to enjoy programming the ARM and assembly programming in general. Thanks for watching today, and goodbye.